Hello. It is time to begin, and I'm very pleased to have we're very pleased to have Michael Vasmer tell us about single shot and measurement-based quantum error correction. Please.
Thanks, Jinkai, for the introduction, and thanks to the organisers for putting on a great conference. I should say that Timo was originally going to give this talk, but unfortunately couldn't make it, so you're stuck with me. Today I want to tell you a bit about a project where our original question was how are we going to do single-shot error correction in MBQC in measurement-based quantum computation. And I'll start by reviewing some stuff that should be familiar on chain complexes and then go quickly through single-shot error correction and measurement-based computation. And then I'll tell you a bit about this formalism we developed to tackle this question and its application to foliated codes. And then I'll also kind of touch on some connections that were kind of surprising to us that we came up with when we were working on this. So this slide's just a bit to fix notation, I think. So we'll have a CSS code. I think we all know what that is. And we have these two matrices, HX and HZ. And we know that we can represent this mathematically if we want to as this chain complex where we have these maps between these vector spaces. And we have this, the composition of the maps is 0, which is corresponding to the commutation of the checks there. And single-shot error correction is something I guess people are also familiar with. But often in, like, if you're thinking about especially the surface code, for example, if you want to deal with measurement errors, you repeat the stabilizer measurements or the code distance number of times. And in single-shot codes, you only need one round of measurements to do fault-tolerant error correction. And then this is connected to something called meta checks, where certain codes of the single-shot property have these meta checks, and we can represent this as this like longer chain complex, where now, as well as the kind of check matrices HZ and HX, we have these meta check matrices, which are just like checks on the checks. So when I measure a syndrome, I can apply this meta check matrix to it and see if the syndrome passes the checks, and I can use this to detect and correct measurement errors. Okay, and then measurement-based quantum computation is a paradigm of computation where we start from this entangled graph state, and then the computation proceeds via single qubit measurements. And so we just take a graph, and then we put a plus state at every vertex, and we apply CZ edges for every edge. And then this is a stabilizer state where you have these stabilizers, which is like X on a vertex qubit, and then Z on its neighbors in the graph. And then you can think of something like this. So this graph is just like this path graph. This is like the kind of teleportation chain for CV cluster states. And we start with this, we make this entangled resource, and you imagine you start with this state here. Then when we measure this, you kind of get this teleportation chain of Hadamard. You pick up a Hadamard and you go like this. And then you can kind of generalize this to do arbitrary computations. And you have to add in also an X plus Y measurement. And in fault-tolerant graph states, so this is kind of, if you want to think about doing kind of error correction, measurement-based quantum computation, you have a graph state with additional structure where certain products of the measurement outcomes are deterministic in the absence of errors. So these are kind of like detectors in your detector error model, if you're familiar with that. And this is just something where you can use these to detect and correct errors. Okay, so now let's combine these kind of things. So there's this concept of foliation, which is a way of making fault-tolerant graph state from a CSS code. So we start with a CSS code, and then we stack alternating layers of the tanagraphs of HX and HZ, and then we connect the corresponding variable nodes in the neighboring layers. So I'll give you a picture of this so you can see kind of how it works. So let's imagine this code, simple code. We have this X check, it's just on all the qubits, and these two Z checks. And then we stack layers of these tanagraphs of these X and Z tanagraphs like this. And then I'm going to connect them like the variable nodes. So these kind of like the check nodes, the variable nodes, and then I connect them like this. And then this thing is known as a foliation of the input CSS code, and it's one of these fault-tolerant graph states. And yeah, an important property of this kind of thing is, this kind of state is we have like this bipartition of the vertices, which is kind of key to what we'll do later. Okay, so with that quite quick review, we can go on to the results. So we observed that these foliated codes, you could describe them more formally as this hypergraph or tensor product of a CSS code chain complex C with a repetition code chain complex R. And so we have like some CSS code chain complex C, and then this is the repetition code is just like a classical linear code, so you could represent it like this. So you have the kind of bits going to the checks and this check matrix here. And then you can define this tensor product of chain complexes like this. So you get this new chain complex, and this one has now kind of 4 spaces and 3 maps, and because you kind of add these two. And the way it works is defined formally, you get like these kind of spaces. So you get these tensor product of these direct products of these, and then you can just derive what the boundary operators have to be of this chain complex, so that you have the right property and they compose to 0. Okay, and we defined this fault complex formalism where we've got this object here, which is this tensor product, and then what we're going to do is associate this F1 space of the primal qubits of the graph state and the F2 space of the dual qubits. So these are the bipartite vertices in that graph I was showing you earlier. I don't have time to kind of derive exactly why this works, but if you're interested, I'm very happy to walk you through the proof afterwards offline. And then this middle map here just turns out to be the biadjacency matrix of the graph state itself, and then you can just get this from the kind of formulas, and you have this, and let's see why this is kind of the case. So you can kind of see here that this qubit here is like connected to this Z-check qubit here, which is kind of like coming from this part of this transpose, and then it's connected to these other qubits via like this R tensor 1, where this is like a weight 2 thing, so you get these checks here. And this might be hard to see kind of live, but once you stare at this, you can kind of see that this must be true. And also, as I said before, we can derive this quite generically for a bipartite cluster state, that it will always work in this way. And then, as with kind of like in analogy with the CSS code chain complex, we have these. So we have these two spaces which are like our qubits, and then we have these kind of like detectors, which are like these, which we associated with this the F0 space and the F3 space, and then we have these two kind of detector matrices, which you can view them a bit like the check matrices of a CSS code. And so, for example, if you plug in the kind of definitions, so this partial 1, which you call this detector matrix, you just get this kind of this structure. And if you're familiar with measurement-based quantum computation with foliation, this will look kind of familiar, because what you get here is that, so if you think of just one row of this, I'm just going to get a copy of like a check of the HX, and then I'm also going to get this part here, which is like a weight 2 thing, and then this exactly goes like this. So in this state, in this check, I have these 4 qubits, which you can see is like the support of like one of the X checks. And then I also get these things. And this might be kind of reminiscent as well with the kind of phenomenological model for circuit noise, if you've seen that, it looks kind of similar. Okay, and now why did we go to all this like effort of writing things in this way? Well, we wanted to be able to use some kind of more advanced tools to analyze these things. So we know that with CSS codes, we can kind of make this connection with homology, and then we have the logical Z operators, for example, associated with this homology group. And the same thing happens in the fault complex here. So we have these things that are called logical correlations, and this is kind of, if you view the fault complex as this measurement-based protocol where it's like an implementation, a fault-tolerant channel between 2 codes, then these are the logical correlations, are the kind of correlations of the input code and the output code. So this is the kind of information you want to preserve. And those look like that. And then you have these logical errors, which are the thing that can disrupt the correlations you're trying to get in your channel. And the nice thing, the way we set this up, is now that you've got this kind of like foliation described as a chain complex, you can then go to this nice paper by Zen and Priadko and just use these kind of formulas to get all the homology groups of the fault complex from the input codes. So now, like, deriving like all these things is just like you can exactly see how they come from the input CSS code. So and specifically, so the homology group, the repetition codes are very simple. You just get like this kind of weight 1 vector. And then this one is just like the logical Z operators of the CSS code, this LZ, and so you see that these kind of these logical errors are coming from the CSS code ones, and then similarly the correlations here come from the X logical operators. So the kind of homology of this fault complex is just coming directly from the input codes. And I've tried to keep this example going so it's not super abstract. So you can see here an example of one of the logical correlations. So this is just like the logical X of the input code, but then like copied into these like odd layers. And this is kind of, you've got this one here, and then you can think of these as the odd layers, and then here's like the even layers. And so you have this, and if you're familiar again with MBQC and foliation, this is exactly what you would expect. And then the logical error, the thing that can disrupt this, is like, so you get like a copy of the logical Z, but only in one layer. And for me, this was quite nice because when I first started thinking about these, it was kind of mysterious to me, like where all these logical correlations and errors came from in the standard treatment. So I found it, at least for me, quite useful to have this like mathematical basis to understand why they were there. And then, in continuing the analogy with the CSS codes, we have the number of primal and dual correlations, which and they can actually be different, which is kind of curious, but it's just saying, you know, you can do like a logical Z measurement in the channel if you wanted to. And then you also have kind of generalizations of the distance to, this is just like the minimum weight logical error. So the minimum weight operator that can disrupt a correlation. But it all kind of like drops out in the same way. And okay, so that up to this point, we've kind of like just rederived foliation, but in like a slightly more fancy kind of framework, which is fine. But then I think the most interesting stuff for me of the project was when we started to kind of see things that I didn't know how to interpret before. So if you just kind of follow the formulas in that paper by Zeng and Priadko, you notice that if the check matrices of the input codes are not full rank, then you're going to get additional contributions to the homology. So for example, here we'll get these kind of contributions, and so this is just kind of plugging in the formulas, but then how do we kind of interpret these? So this G matrix here, so this is like the HX matrix, and we want something G that's in the kernel of the transpose. So this is like a combination of stabilizers that if I kind of multiply them all together, I get the identity. So it's like, so for this one, for example, it's just like, you see if I add all these rows, mod 2, I get 0. So this is like it's like a product of stabilizers that multiplies to the identity. And then you get a kind of conjugate operator here, which is like basically something that's, it's in this space, but it's not the syndrome of a valid error. But to make it more, and the thing that's quite nice about these is that if you consider a code where you have like a very large number of stabilizer generators whose product gives you their identity, this is exactly the kind of thing that was studied by Craig Gidney in this paper on stability experiments, which is a procedure you can do where you make a surface code with, so you can multiply all the checks and you get the identity, and this allows you to kind of like benchmark lattice surgery computations. And these codes kind of popped out of the formalism, and so we found that to be quite interesting. And to give you an example, so this is just like, you know, in this cluster state here, I have this operator, which is like, basically it's telling you that the product of these kind of stabilizers is the identity, and this is something that if there's no noise, this should be preserved by this should be deterministic. And then the thing that can flip this is basically like, you can think of this, it's like a time-like error. And so it's a way to kind of, you get these stability experiments quite naturally. And yeah, I think I will have time. I'll return to another interesting part about these at the end. But I just want to go back to the original motivation, which was the constructing codes, foliated codes of the single-shot property. So we have this chain complex here with this 5 spaces because we have the meta checks. And then now if we want to understand how to foliate this and how it all works, we just plug it straight into the definitions. So all that changes is now we get like this extra row in the detector matrix because of this MX. So we now have these rows were there before, and we have this extra one. But you see that like these meta checks are just like naturally incorporated into the detectors. And now once you've got this framework, you don't really need to think too much about how to exactly do error correction with the single shot MPQC, because it's just kind of naturally falls out of the formalism, and you just use this detector matrix in your decoding. Okay, that's what I just said. And yeah, so why we like this is that we found this framework significantly simplified the construction of the graph states for the simulations and made our kind of simulation pipeline for this significantly simpler, because we can just start like constructing the things we want to simulate just by taking like tensor products of chain complexes, and then we just have to do Gaussian elimination to get logical representatives, but it's all very, very nice. And then we use this to do some Monte Carlo simulations to estimate the error thresholds of 3D and 4D toric codes, which have the single shot property in 2 noise models. So first you have like phenomenological Pauli noise, and then we also did, this is work that I did while I was working at Xanadu, and so we were looking at Xanadu's architecture for fault-tolerant quantum computer that's based on GKP qubits. And in both noise models, we have this fault complex structure, then it's just kind of changing what the channel is at the individual qubit level. And then we kind of use a standard approach to decode this thing, which is an overlapping window decoder. Which is, so I don't unfortunately have time to explain that now, but this is a kind of standard approach to decoding, and the nice thing is that we recover the kind of best previous results for these codes, as a special case of this approach. So if you use like a 1-1 overlapping window decoder, you get this Higgett and Breukman result. So here's some of the plots from the paper. This is quite a busy plot, so let's just concentrate on the left-hand side here. So this is like the Pauli noise case, and what I'm plotting here, if you look at the top left, we have the error threshold here as a function of the number of rounds of error correction, where that's just like a round is like I measure all the stabilizer generators. And you see here, so we have this, as we kind of increase the number of rounds, the threshold starts at a high kind of value, and then it kind of decays but plateaus. And you see here that basically this W parameter is the window size in the overlapping window decoder, and as we increase it, we get like a significant boost in the threshold. The previous best result was down here about kind of 7.5%, and then we're getting closer to like a 10 here. And this is a noise model where, so for phenomenological noise, we just have errors on the qubits and errors on the measurements. And you get a similar thing for the 4D toric code. And then we also on the right have the Xanadu noise model. And in that one, the things are kind of inverted because we're just using a different scale for the errors in terms of decibels. But you get kind of similar style behavior. These simulations, as I said, were made like much simpler to write because of the fault complex framework. Okay, and the last thing I want to tell you about is that we also kind of were thinking about stability experiments for high-dimensional topological codes in this framework. So if we apply the formulas from earlier, we have the primal distance for the 2D toric code, and you foliate it with a distance D repetition code, so a distance delta repetition code, sorry. And then the distance here is just the minimum over the x distance of the input 2D toric code and the length of the repetition code. And this is kind of, telling you about this thing where, okay, I need to have D rounds of measurements in order to preserve the time-like distance, and you kind of see this here. But if I consider instead of 4D toric code, something quite interesting happens, because now my primal fault distance here is the minimum over the x distance of the 4D toric code, then I get delta times the root of the x distance. So you see here that even if I choose delta to be 1, I still have a macroscopic distance. And so this is telling you that in these high-dimensional topological codes, we can preserve this like stability experiment correlation even for like constant number of rounds. And so I think this gives like quite a strong evidence that you would expect to be able to do fault-tolerant lattice surgery with kind of constant time overhead in these codes. And this is something that I'm currently investigating, but I think it should be possible. Okay, so just to wrap up here, I wanted to point out some related other work, because there's been lots of nice work on formalizing fault-tolerant protocols recently. So there's, we were very indebted to this paper by Newman, De Castro, and Brown on kind of connecting homology and fault-tolerant graph states. And then there was also a concurrent work where people looked at this chain complex foliation from the perspective of condensed matter physics. And then I wanted to point out in particular this works by Cy Quantum and then Ying Li as well, which are kind of quite relevant and have similar ideas. Okay, so then finally, I just wanted to end with a few open questions from my point of view. So I presented to you in this talk the fault complex from the perspective of measurement-based quantum computation. I think it's kind of easy to see that this also generalizes to kind of phenomenological noise. But then the question I have is, like, how does this relate to circuit noise, and can we use it to kind of improve the decoding in that case as well? And in that case, what's going on, I think, is that this middle partial 2 map is related to the gauge group of the subsystem space-time code, if you know what that is. And I think hopefully we can extend this formalism. And then also, interestingly, all these results we use from the Zhang and Priadko paper, you don't have to have a repetition code as input. You can use any linear code. So we could equivalently make some fault complexes with these other linear codes, but then I'm not exactly sure what the kind of operational definition, like interpretation of this should be yet. And then one question I've always had is like this paper on fault-tolerant graph states beyond foliation, and perhaps we can kind of recover them in this like more general formalism. And then of course you could say, okay, well I can start making, I can take other product constructions to using like balanced or lifted products. And like, does this give me kind of interesting graph states or more kind of efficient fault complexes, as it seems to do in the case of CSS codes? So I think with that, I'm out of time, and I'd like to thank you for your attention.
Thanks for the nice overview. I have a question on the single-shot lattice surgery indication, like the property that you can foliate like just with a constant size repetition code. How general is that? And like, in particular, can you prove something like if your input code has confinement, you always can do that, or if you have like a meta check of a certain rank, can you always do it?
Yeah, so I think it's going to be like related to the distance of the meta check code. I don't know if that's like a well-defined concept exactly, but you kind of know what I mean. If I wanted to like spoof the meta checks in the 4D toric code, I need to do like a loop of edges like all around the handle of the 4 torus. And so I think if you know, so this distance is like, you know, square root d basically. But if I had like a code with like good meta check distance, I wouldn't lose any code distance when I did the foliation. So I think it is general and will probably hold in like things like four-dimensional product codes. I think would always hold this kind of thing.
So self-correction is another interesting property of codes that's sort of adjacent to single-shotness. Is there any way to, or do you expect there to be any way to think about self-correcting codes using this sort of chain complex formalism? Is there a way to express
so
it?
I think people have definitely thought about this, and there was an interesting talk earlier about how this confinement property that Julio mentioned exactly kind of implies self-correction if you have linear confinement. So I think yeah, and I think perhaps maybe you could use this formalism to think about those questions. But, yeah.
Thanks.
Further questions, we can thank the speaker again.